right down the street at CU Boulder and LASP. Thank you to the organizers for inviting me to speak today. I'm going to be talking about advances in 3D exoplanetary climate modeling. And I suppose a lot of what I'm going to say is going to boil down to making an argument of why 3D models are useful for modeling exoplanets. I know this is NCAR, so perhaps I'm preaching to the choir to some, but it's still a point that needs to be made at times to the community. So it should come at no surprise that Earth, all the planets, all the exoplanets are three-dimensional objects, actually. They're rotating spheres covered in a fluid envelope. And atmospheres are governed by well-known physics. So we're not solving for quantum gravity here. We understand fluid dynamics, and we can code it up quite well. Same with radiative transfer. We understand radiative transfer well, and we can now make approximations to radiative transfer that's fast enough in our GCMs to use in a computationally efficient manner. We understand convection, we understand clouds, although subgrid scale processes of clouds and GCMs is perhaps a white whale of GCM modeling at this point. But we can stitch all these pieces together and we can simulate atmospheres with 3D general circulation and climate models. And they look a little something like this, but actually this is even a little outdated because modern GCM grids don't use a lat-long grid because they converge at a singularity at the poles. They use, imagine a soccer ball, a tiled spheres. But in any rate, you have a series of columns, several thousand columns at minimum, in which you calculate vertical physical processes, radiation, convection, cloud condensation, surface processes, etc. You do that calculation for every single one of the columns, and then in the intermediary step, you calculate the fluid dynamics of where the wind is blowing, where things are advecting, where heat is moving, and you iterate back and forth between column calls for physics and then global calls for atmospheric dynamics to predict your climate. And we say 3D models, but perhaps we should even call them 4D models because time is a dimension as well to study, the variability. So the move to 3D models has come slowly for planetary and exoplanetary communities. One, especially for exoplanets, is a very much data-starved environment. So using 3D models perhaps can seem as overkill for the amount of data we're returning. But two, have been limited by our technology. So the first easiest thing to do, and is still done, is calculate the so-called equilibrium temperature of a planet just based on the insolation and some assumed albedo and black body emission. For the last several decades, we've used 1D models to great effect, both 1D radiative convective models along with 1D energy balance models, perhaps equator to pole or pole to pole. And then finally, in the modern age, with modern supercomputers, we now can use 3D climate models and run fairly large numbers of 3D models. But the issue still remains of when you're looking at your problem, whether to use a 1D or a 3D model, because just because we have supercomputers and we can run dozens of 3D models, well, you can still run thousands and thousands of 1D models depending upon your problems. So numerous 3D GCMs are now used to simulate planets and exoplanets. So of course, NCAR CESM goes at the top of the list because we're here at NCAR today. But also the NASA GISS Model E, which has been, they have a team there working to convert it to the Rocky 3D exoplanet type model. The UK Met Office, actually, this is to say the unified model, not the united model. The LMD generic climate model and their family of, they have LMD Mars, LMD Saturn, et cetera, et cetera. They're arguably the leader in the field. They've had community support, or institutional support for that model for a couple decades, so they're leading the field, I would say. And then various GCMs of intermediate complexity, meaning a dynamical core with simplified physics. Various flavors of GFDL FMS, PLOSIM, MIT GCM and Spark, used a lot for gas giants, a few others. So 3D models are now becoming commonly used for these type problems. And the first lower hanging fruit, I should say, is to simulate solar system objects. So modern Earth, obviously, we have up to the second weather data that you can compare models with. But even if we go back to the deep paleoclimate Earth, it's almost like another planet entirely. Thinking about the climate history, snowball Earth events, the faint young sun paradox, why did the early Earth stay warm despite the faint young sun? So GCMs have been applied to those type paleoclimate problems for Earth. Also for Mars, we have an army of satellites and rovers around Mars such that present-day weather phenomenon on Mars is something you can model realistically with a 3D model and compare it to real data. High cloud formation on early Mars, dust storms, etc. And then the climate history of Mars continues to be one of the great problems in remaining in planetary science, because you have the same faint young sun paradox, except Mars was so much colder than the Earth, received so much less insolation than the Earth already. So the faint young sun paradox becomes exacerbated, and it still remains unresolved today. And that's something we can use 3D models to study. In particular, they're useful because the geology on Mars is exquisitely left remaining for us to see. So you can use a 3D model to try to find solutions to the faint young sun paradox for Mars and see if your precipitation patterns, for instance, match up with the geology on Mars. So those are some of the things 3D models are used for Mars. Venus, not worked on quite as much. It's notoriously difficult to model to capture the upper level superrotation. It's a very thick, hot atmosphere, which models tend to not quite like numerically at times. You have the sulfur hazes. People also think about the climate history of Mars. There's an idea that with with Venus's slow rotation rate, could have affected climate significantly in the distant past, where the fainter young sun actually might have helped it be more habitable because it's clearly too hot today. Titan, Cassini was up for almost 2 decades, so 3D models have attacked the ubiquitous haze layer, other things like the formation of equatorial dunes on Titan. There's also GCMs used for gas giants, which I know less about. But then, so from these solar system objects, we move to the weird, wide world of exoplanets, which is either a blessing or a curse from a climate science perspective. So it's a blessing because there's perhaps an infinite variety of new worlds and interesting atmospheres and situations we can study with our models. But it's a curse because it also can let us indulge ourselves in exploring these worlds for which we're extremely data starved at the moment. And we're hopeful that we will get this data on these worlds, but it seems as the JWST launches keep getting pushed back and back and back, and LUVOIR seems but a distant dream, it's not clear exactly when this good data is going to come. It'll come eventually. Perhaps I might be retired by then, but it'll come eventually. So as of today, there are 4,126 confirmed exoplanets on the NASA Exoplanet Archive, found through different methods we've already talked about. There's another 1,600 plus test candidates which are awaiting confirmation. Of these, there are 55 considered in the optimistic habitable zone and 21 in the conservative habitable zone. I'm not going to get into the habitable zone. Jim is going to talk about that in the next talk. But what do we mean by habitable? Generically, we think of the abundance of liquid surface water. And now that doesn't mean that other worlds like Europa or microbes deep beneath some rocky planet interior to the habitable zone might not have life somewhere. But if we're going to detect life on an exoplanet or detect signs of life, life must exist at the surface, and it must be able to modify its atmosphere in a meaningful way that we can detect in our spectra. That is why that defines the habitable zone. So it's more of the search area that we're looking at. So this was already shown yesterday, but I'm going to harp on it one more time. So 3D GCMs have already proven important for explaining observations of hot Jupiters. So the regime of planets that we're best able to get good enough data on are the big ones and the hot ones that are close to their star, so hot Jupiters. This was shown yesterday, so the offset in the thermal emission phase curve from these worlds, from the substellar point, matches up very well with GCM models of, which all tend to, numerous models all agree with the result that these hot Jupiters would have a strong super-rotating jet at their equator, which advects that heat eastward of the equator. So rather than having your hotspot, say, you might expect it to be right on the substellar point or perhaps lag behind due to thermal inertia. Instead, it is ahead of the substellar point due to this super rotating wind. So in the first problem where we actually have exoplanet data that's good enough to say something with the 3D model. The 3D models have come in and provided a good explanation. So my interests lie in terrestrial planets. There is a wide variety of states for terrestrial planets that we just see just from our own solar system, from habitable worlds with oceans, planets like Earth, to perhaps we can imagine early Mars as a water-limited place with some water, but generally arid, but still habitable. We know Earth has been experienced snowball Earth events where it's completely iced over. Atmospheres can be thin, they can be thick. We can imagine Earth in the future, not just from anthropogenic climate change, regardless of the CO2 we put in the atmosphere, the sun is going to keep getting brighter, and it's going to cook us in 1 billion or 2 years either way. So these are the things, the evolution of planetary atmospheres is something I like to think about and use 3D models to study. So first, a word of caution about all the terrestrial exoplanets you see in the news. So in the popular press, in your favorite mainstream media source, you'll see headlines much like our own: Earth-like, alien life, water, Earth-like, Earth-like. And then, so you don't trust the mainstream media, of course, so you look at Nature magazine for their headlines, and you see the peer-reviewed journal articles: temperate exo-Earth, temperate orbit, 7 temperate terrestrial planets, temperate. It's a pet peeve word of mine at this point. So when you're an Earth scientist, so I come from a Earth science background, atmospheric science department. When you hear temperate, you may think of the Köppen climate system, or the Köppen climate classifications, mid-latitude climates, temperate deciduous forests, or Earth-like. You think Earth, but when you see these headlines, even in a peer-reviewed Nature article, when an astronomer tells you Earth-like and temperate, what they really mean is the mass and the stellar flux are probably within about a factor of 5 of Earth. It was not, so, you know, it's a kind of it is what it is. You know, you got to get attention somehow. So be cautious of all the things you read in the press. So, and for example, here's a recent, I'm guilty also. I was involved in this recent project, and this is a Time magazine headline. NASA may have found Goldilocks of Goldilocks planets, and you'll see an accompanying gorgeous image, artist rendition. Well, what do we really know? More like this. It's kind of an orb in the sky at the moment. So we know the mass. If we're lucky and we have transit and radial velocity measurements, we know the mass, the radius, the orbital period. We know something about the star, the star's luminosity, its stellar spectra, so we know the incident stellar flux on the planet. Things we generally don't know. Atmosphere, except for the very limited cases where we have spectra for hot Jupiters, but this is not the case for terrestrial planets. The atmospheric composition, surface properties, rotation rate. There's an asterisk by rotation rate because for tidally locked planets around low mass stars, we have an inference of their rotation rate by assuming tidal locking that they could be in either synchronous or resonant orbit. So that helps us illuminate one thing we don't know. So what do GCMs, what can they tell us about terrestrial extrasolar planets? So one of the key thing for GCMs is not that they do all the physics the best, but the fact that they couple all the physics together, so they're interacting together. So for these different worlds with different radiative forcings, perhaps different atmospheres, different rotation rates, all of these, we can discover novel and interesting physical processes via the self-consistent coupling of these processes as the radiation interacts with the gases in the atmosphere, interacts with convection, interacts with condensation of clouds, interacts with the large-scale circulation of the atmosphere, et cetera, et cetera. So when we think about terrestrial planets where we don't know much beyond their bulk properties, we can use our models to assess their potential for habitability, if liquid water could possibly exist. So we can take our GCMs that have been sufficiently made flexible enough, but they're all generically have started from Earth climate modeling communities and been moved to the exoplanet communities. So we feed in our knowns, the solar constant, the spectral energy distribution, the size of the planet. If it's around an M dwarf, maybe we know what the rotation rate is. If not, omega would go in the unknown category. And then we can vary expected parameters, such as the total pressure of the atmosphere, the amount of greenhouse gases, obliquity, eccentricity, the surface composition. And then our models can predict a self-consistent climate So we can vary these unknowns and simulate a planet and say, okay, well, this planet can maintain habitable conditions with a wide variety of atmospheric compositions. Perhaps a good target. Or this planet cannot. This planet's going to be too cold, and regardless of how much CO2 you put in the atmosphere, it's going to freeze over. It can give us first order ideas about the potential for habitability. So the 3D models help us self-consistently simulate important climate feedbacks. For habitable worlds with water, those being the water vapor greenhouse feedback, which tends to make climate too hot, and ice albedo feedback, which will drive climate to be too cold. And 3D models are also useful for trying to deduce potential observables. So one, producing self-consistent vertical profiles. You could take them along the terminators in your 3D model, simulate transmission spectra. And then one of my favorites being phase curves. So 3D models with spatial and temporal resolution. You can see what the thermal emission and reflection looks like over the course of the orbit of a planet as well. So, but in terms of climate, in terms of habitable planet climates, we think of water. And water is special because it is stable in all three thermodynamic phases. Solids, liquids, and the most boring, gases, of course. But each of these thermodynamic phases drive climate in interesting ways. So water is actually a destabilizing force for climate. It's great for life, but for climate, it can wreak havoc. So for the Earth-like planet here, you have liquid surface water, which is a broad-band shortwave absorber, water vapor, which absorbs in the near IR, and is also a strong greenhouse gas. Clouds, which are shortwave reflectors, but if there are low clouds, but high clouds, cirrus clouds, institute greenhouse effects that can go either way. Surface snow and ice adds to the albedo of the planet, and as you can see from the Earth, there's great spatial variation between where your clouds, your ice, also your water vapor are, which affect climate. So for warm planets towards the inner edge of the habitable zone, it's really the water vapor and the clouds which we're most concerned about. So the water vapor greenhouse feedback, so water vapor is greenhouse. You get a little bit warmer, more water vapor gets in the atmosphere. It makes the greenhouse effect stronger. You get the planet gets warmer, you get more water in the atmosphere, et cetera, and it can drive a planet into a runaway. So 3D models are great because they can predict spatially inhomogeneous relative humidity and cloud patterns, which it turns out are very important for simulating the climates of these hothouse planets. So for a simplified diagram, you can think about this famous paper from Ray Pierre Humbert, thermostats, radiator fins, and the local runaway greenhouse, where he argues that if you just consider the Earth's tropics, the Earth's tropics are so humid they could perhaps lapse into a runaway greenhouse if you didn't have the general circulation of the atmosphere resulting in the subsiding zones at 30 degrees latitude from your Hadley cells, which are dry, and are the radiator fins, which allow OLR to escape to space. So 3D models have shown this in the runaway greenhouse problem for Earth, that the low relative humidity regions help cool the Earth off, and that's inherently a 3D effect. And then it's not to mention clouds as well, which add to the, clouds can go either way because clouds add to the reflectivity of the planet, but it's unclear if clouds will increase or decrease depending upon different radiative forcings. So on the other edge of the habitable zone, we have cold worlds, and you see I've added one here at the bottom being a CO2 atmospheric collapse. So towards the outer edge of the habitable zone, or early Mars, we may think about denser CO2 atmospheres. So not just Earth, but Earth's composition, but you can imagine a multi-bar CO. What if we switched Mars and Venus in the solar system? Would with Venus with its, of course, that changes the whole evolutionary history here, but just imagine Mars with a dense CO2 atmosphere today like Venus could perhaps stay warm. But there's also the problem, which is a 3D problem as well, of atmospheric collapse. There was a recent 3D paper from the LMD group where they looked at these type CO2 atmospheres and found that collapse of condensation of CO2 onto the poles in particular is a problem near the outer edge, something that isn't captured in lower dimensional models. And also thinking about the more immediate problems of, say, glaciation, snowball glaciation, things like the three-dimensional treatment of dynamic ocean models, which are very expensive to run. This is from a Jun Yang study with CESM. Ocean currents and the motion in moving in 3 dimensions help determine whether climate may be going into a snowball or not. So I've tried to make the argument here that there's important climate processes, whether you're thinking about planetary science, the history of Earth, the history of Mars. There's important 3D processes which we need to treat. And then likewise, when we think about exoplanets and a diversity of forcings and compositions, these 3D effects also play into our understanding of these atmospheres and what observables we may find. So one of the top targets are planets around M-dwarf systems. So they're not without their problems, but at the moment, by default perhaps, they are where we're going to be looking for terrestrial planets. So the M-dwarfs are small, they're dim, they make up about 70% of the nearby stellar population. Planets are in short period orbits. We've discovered a bunch of terrestrial planets around M-dwarfs. So they're probably our best shot at observing a terrestrial planet in the next decade. From a climate and atmosphere perspective, there's interesting physics and dynamics that occur on these terrestrial planet atmospheres. As a caveat, as I'm sure many in the audience know, M-dwarf stars undergo a vicious pre-main sequence phase and are also much more active than our sun. So it's up for debate about whether these planets retain their atmospheres, how they're sculpted by photoevaporation, stellar activity, and the like. So whether they end up being good targets or bad targets, hopefully we'll have some ideas soon with JWST, because for terrestrial planets we will be able to make hopefully based on phase curves, for some planets we might be able to make an up or down. Probably the best we can do is make an up or down vote on whether a planet has an atmosphere or not. So that would be a first order question to answer. But because we have these awesome models and the funding lords have allowed us to indulge ourselves in what these planets might look like if they do have atmospheres. So they have interesting physics and dynamics, as I said, one thing being driven by the assumption of tidal synchronization. So M-dwarfs are so dim that habitable zone planets must be so close to their star that we expect them to be tidally locked, likely in synchronous rotation, which would result in the so-called eyeball climate state that's been conjectured, where the same side of the planet always faces the star. So you might have ice completely on the night side with a hot spot on the day side. Another thing that comes into play is the fact that the spectra of M-dwarf are so red. You can see the comparison between the Sun and Proxima Centauri. And then also M-dwarfs have reduced near UV fluxes but enhanced E and X UV fluxes, which will affect photochemistry as well. So from a climate science, the climate point of view, we can think of this eyeball climate state in terms of the same forcings we talked about before. Clouds and shortwave reflection take on an outsized role for these type planets, assuming that water is available, because the changes in the circulation result in an intense upwelling on the day side. So a large reflective cloud that may exist on the day side of the planet. The lofting that results in the clouds also results in enhanced amounts of water vapor that enters these atmospheres as well. Snow and CO2 condensation would generally occur on the night side, so the effect on the albedo from snow and ice is perhaps more limited than you would see for a rapidly rotating planet. The clouds, though, have an outsized importance. So this is a couple movies just comparing between the Earth and then a slow rotating planet. So the dynamics of the slow rotating planets on the right would also be applicable to, say, a Venus-like planet around the Sun that just happens to have a slower rotation rate. So on the top we have an equatorial slice of the water vapor in the atmosphere, and then on the bottom we have the cloud water column, and you can see the clear differences. This eyeball climate on the right-hand side with this thick cloud just sitting there. Looking at the water vapor as a tracer, we can see how much deeper the water vapor penetrates into the atmosphere, sourcing this cloud. And these are driven by the three-dimensional change effect. The changes to the atmospheric circulation, because the slow rotating planet has a very weak Coriolis force, which begets this thermally direct circulation with rising motions on the day side and descending motions on the night side, rather than having multiple cells like we do on Earth today. So, but this effect is also dependent on the specific rotation rate. So it's not just the same thing for all tidally locked planets, for instance. If we increase the rotation rate, you start increasing your Coriolis force until eventually you start smearing out the clouds and preventing the water from penetrating deep in the atmosphere. The same plots, cloud water column on the bottom, water vapor along the equator at the top with increasing rotation rates. And we can see how eventually that cloud deck starts to be broken up when you get into the regime of rotation rates and on the order of 5 days or so. So one of the other things you can learn, I mentioned this earlier, is with 3D models, is about phase curves. So that's, I think, one of the most useful things, perhaps, not just for thinking of terrestrial planets, but also when we think about the type of planets that we can observe better, the larger, warmer ones, is looking at the change in the thermal emission from a planet as it rotates around its star. And this becomes particularly interesting when thinking about these tidally locked planets, because the tidally locked planets have more of a dichotomy between their day side and their night side. So a thermal emission phase curve of the Earth around the sun, first of all, would take a long time to observe, because you have to get multiple orbits to feel confident in your result, has a much flatter thermal emission phase curve than if you took Earth and put it around in a tidally locked situation, due to this day-night dichotomy. And some of our research has found that if you look at clouds on the bottom and then we have OLR on the emitted thermal flux at the top, that clouds play a very large role in dictating the outgoing long-wave radiation from these worlds. So clouds, and not just any clouds, but high clouds, cirrus clouds, which can be difficult to model, have an outsized role in determining thermal phase curves for terrestrial planets. But I would also expect that the cloud properties on larger, hotter worlds would likely play a similar role of outsized importance in modifying thermal phase curves. So this is some work done by one of Jim's former students, Jacob Hock-Misra, showing how different thermal phase curves, thermal phase curve patterns can be used to differentiate these different rotation rates, with fast rotators having a flipped thermal phase curve versus slower rotators, and then intermediate rotators as a function of the phase, shown with the cartoon at the top. So I think that phase curves are one of the useful things for 3D models moving forward, both for terrestrial planets and also for the larger regimes. I guess as I'm running out of time here, I just wanted, because this is an NCAR meeting, I just wanted to highlight very quickly some of the recent NCAR modeling related works and various collaborators and associates around the world who use the NCAR model to simulate extrasolar planets. There's a number of us in the US, and there's also several groups in China as well who make much use of CESM. So Ravi Kaparapu and Jacob Hock-Misra and I published a series of papers on the climates of these, potential climates of these planets, terrestrial planets located around M dwarf stars, with part one thinking about moist greenhouse and runaway greenhouse processes in the inner edge of the habitable zone. Part two looking at the circulation of these planets in detail, the differences between how rotation rate drives different circulation regimes. Part three thinking about these thermal phase curves and how different patterns of thermal phase curves at different rotation rate regimes may show differently for different climate states and give us clues into what these climate states actually are. Another paper in the works, bigger project in the works from a colleague, Thomas Fauchez, which is an intercomparison project for the TRAPPIST-1 system, where we're going to compare multiple models, both LMD, CAM, second row, Rocky 3D, and then the United model, and anybody else who wants to join. A recent work by a student at Goddard, Gabriela Suissa, looking at the recent planet discovery, TOI 700D, thinking about patterns of water vapor and clouds and their resultant spectra, both transmission spectra, and then on the right, phase-dependent spectra using the Goddard's planetary spectrum generator. Dorian Abbott's group at the University of Chicago has made a lot of use of the NCAR model to study a variety of different effects of radius and gravity, et cetera, with his postdoc, Tad Kamasic, and students as well. So Dorian continues to use the CESM model. Jun Yang's group at Peking University, Jun was a postdoc with Dorian. So he uses an earlier version, I think he used CCSM rather than CESM. But his calling card of research is he uses the dynamic ocean model feature in CCSM to study planets, and also organized one of the, probably I think the first exoplanet intercomparison with the plot shown at the bottom, trying to compare relative humidity and clouds amongst the different codes. Howard Chan, who's a very talented grad student at Northwestern, and I think also was a student of Jim's, he's been using WACM, if anybody here is familiar with WACM, to do some of the first coupled photochemistry studies of planets, or terrestrial planets around M dwarf stars. And then an incomplete list of other papers looking at high obliquity planets, ocean heat transport, aquaplanets on eccentric orbits, et cetera, et cetera. So this is a very incomplete list. There's even more papers out there. To conclude, the take-home points, so the universe is teeming with planets. Even Earth-like, quote, Earth-like planets can be pretty weird. Habitable surface conditions are a result of complex astrogeophysical and climatological processes, which are all coupled together. The use of 3D models to attack exoplanetary science problems is exploding, both for habitable worlds and for uninhabitable worlds. NCAR CESM is already being used by numerous researchers to study exoplanets. However, I would say that we're lacking unification of the people using CESM. There's a number of groups and we're all kind of doing our own thing. Perhaps that's something we could work on. So the next steps, so habitable planets are fun, but some of the more recent results with what we're going to be capable of with JWST are somewhat discouraging. So I think we need to try to adapt. If we want to, it's fun playing around in exoplanet land, but if we really want to be relevant to data, we need to start adapting our codes to meet JWST observations, which means hotter planets, larger planets. I think clouds and hazes are also a point that we need to focus on more. So as far as CESM, I would suggest CESM coupled with KARMA, which is already on the trunk, could be particularly well suited to be adapted to taking on some of these exoplanet problems in the era of JWST. So that concludes my talk. Thank you for inviting me.
Thank you very much.